Welcome back to the channel. This video is on engine management fundamentals. So leading on from the last video, this is section 4.3, exhaust gas recirculation, EGR. Exhaust gas recirculation, EGR, is a technique for reducing the formation of oxides of nitrogen oxide. A small amount of exhaust gas is rerouted back into the combustion chambers during diluting the combustible mixture and lowering combustion temperatures. You remember that excessive combustion temperatures is also the cause of nitrogen oxide formation, as we looked in the other book, because nitrogen and oxygen are in the air. When you high pressure and high temperature, then they combine together to find nitrogen oxide formation. EGR is necessary to properly control emissions in almost all carbureted engines. Fuel-injected engines can often do away with EGR by maintaining proper control of the air-fuel ratio and treating the exhaust with a three-way catalyst. Section 4.4, exhaust gas after-treatment. As I discussed above under 3.2, effects of air-fuel ratios on pollutants, precise control of the air-fuel ratio alone is not enough to produce adequate reduction of control of engine exhaust pollutants. While this precise control is essential, the necessary reductions require additional treatments of the exhaust after it leaves the engine. After treatment, i.e. catalytic converters. A variety of methods of exhaust gas after treatment have been employed as the allowable levels of pollutants have been forced lower. All rely to some degree on particular exhaust characteristics to function properly, so the success of all depends on precise control of the air-fuel ratio. Air injection reaction. One of the early approaches to reduce emissions was air injection. An air pump, commonly referred to as a smoke pump, delivers air into the exhaust manifold. Adding air tends to burn HC hydrocarbons and CO as they exhaust exit from the cylinders, reducing emissions but increasing underhood heat. You'll find air injection on most carbureted engines and even on many United States fuel-injected engines. But Bosch fuel injection controls fuel delivery with enough precision that air injection is seldom necessary. It is used only on the largest Bosch-equipped engines. So this is the next important, most interesting bit. Catalytic converters. So this is the bit we want to find out about. So let's take a deep breath and then think about this one. Catalytic converters. Catalytic converters are installed as part of the exhaust system located between the exhaust manifold and the tailpipe. The interior surfaces of a catalytic converter are coated with special materials catalysts that promote additional chemical reactions with the pollutants in the exhaust gas and convert them into less harmful substances. Let me read that again. Catalytic converters are installed as part of the exhaust system located between the exhaust manifold and the tailpipe, exhaust pipe, silencer. The internal surfaces of a catalytic converter are coated with special materials, catalysts, that promote additional chemical reactions with the pollutants in the exhaust gas and convert them into less harmful substances. Oxidation catalysts make use of excess air supplied by an air pump to oxidize carbon monoxide and hydrocarbons, add oxygen, and convert them to carbon dioxide and water. That's interesting, isn't it? Because it takes more C from the H. Oh, that's more. That's weird, isn't it? It can only do that by. It says oxygen catalysts make use of excess air supplied by an air pump to oxidize CO and HC. But the only way to do that surely is to burn them, that's combustion, and convert them to CO2, O2 and H2O. Reduction catalysts work without the addition of excess air to reduce nitrogen oxide. The combination of an oxidation catalyst and a reduction catalyst in one housing, a dual bed catalyst, produces a complex series of chemical reactions which produce all three pollutants. A disadvantage of dual bed catalysts is that they rely on slightly rich air-fuel ratios, which increases fuel consumption. To work most efficiently, the converter must be as hot as possible. For this reason, the best placement is in the exhaust system as near to the engine as possible. In addition to operating at high temperature, the reaction themselves produce heat. Most catalytic converters require heat shields to prevent combustion of something under the car. Even so, drivers are cautioned to avoid parking a hot car near anything combustible such as tall grass or dry leaves. Alright. Then we got the picture here. I know on my Fiesta the cat converter is right by the exhaust manifold. Catalytic converters treatment of oxide generates heat, so converters has heat shield to protect car and anything combustible under the car. Three-way catalytic converters. The most advanced and by now the most widely used catalyst is the three-way catalyst, so called because its chemical reactions operate to lower all three controlled pollutants to levels which could not be achieved previously. Remember that in complete combustion, hydrocarbons, Hc plus oxygen, O2 plus air, nitrogen. Nitrogen is just in the air, he's saying, equals CO2, carbon dioxide, plus H2O water plus nitrogen. So nitrogen just goes in and out the engine without no problem. Incomplete combustion produces carbon monoxide instead of carbon dioxide, that's CO instead of CO2, and high temperature combustion as from a lean mixture, and high temperature combustion as from a lean mixture, and high temperature combustion as from a lean mixture combines nitrogen plus oxygen to form nitrogen oxide. And we refer to my other video, I've done a chemical video. The problem with nitrogen oxide is that it goes into the atmosphere, then it mixes with water, and then you get nitric acid rain. So you got acid rain from it. I don't know, nitrogen oxide also sounds like it wouldn't be very nice stuff to breathe in. I don't know, it mustn't be that nice. In the three-way catalytic converter, we want to 1. Add oxygen to oxidize the hydrocarbons and carbon monoxide to make H2O, that's water and CO2, and 2. Take away oxygen to reduce nitrogen oxide. 2. Take away oxygen to reduce nitrogen oxide. Separate it into nitrogen and oxygen. Oops, that seems a bit weird. And take away and separate it. Okay, that was the end of the sentence. I thought it was a bit more. Oh dear. See if I can get to section 5 then. You might think it's as simple as taking the oxygen away from the nitrogen oxide and giving it to the carbon monoxide. Simply stated, that is what happens in some three-way catalytic converters. The catalytic material in the converter helps these chemical reactions take place. In order for reduction, taking away oxygen from nitrogen oxide to match oxidization, adding oxygen to CO and hydrocarbon, the proportion of the gases in the engine exhaust must be controlled very closely. That means the intake air-fuel ratio must always be in the narrow range near stoichiometric lambda equals 1, or an air-fuel ratio of 14.7, wasn't it? 1 part of air to 1 part of fuel. In some three-way converters, oxygen is pumped in after the reduction to further enhance oxidization. Oh, right. Figure 5.1 illustrates the degree of emission control afforded by three-way catalyst on an engine running very near the stoichiometric ratio. You can see that if the air-fuel strays from lambda equals 1, the proportion of exhaust gases, hydrocarbon, carbon monoxide, and nitrogen oxide, exiting the converter changes. As the fuel-air ratio becomes leaner, hotter combustion temperatures causes increased production of nitrogen oxide. A rich mixture will produce an excess of hydrocarbons and carbon monoxide. Wow, so this, I might come back. I think what I'm going to do, I'll come back and do this video, this table again, because it's quite tailpipe exhaust, that's it, after three-way converter. It's a bit hard to see that, sorry, I wasn't ready for this. Figure 5.4, oh yeah, look at the nitrogen oxide. Oh, so this is tailpipe exhaust of the three-way converter. Control, that's the fuel. So the bottom of the graph is air-fuel ratio, then the lambda, and then the levels of hydrocarbon emissions are those three dotted lines. I can't show you a bit more. Blimey. Tailpipe exhaust of a three-way converter. I think I'll come back to this graph then. When I'll just come back to this graph in the next and do a special vid. Three-way catalytic converter treats three exhaust gases, HC and CO2 are oxidized. Nitrogen oxide is reduced, so tailpipe gases meet emission limit. Engine can be turned to stoichiometric air-fuel ratio for better drivability and economy. Compare with untreated exhaust. Figure 4.3. Oh. Did I do this? I just repeat this. Figure 4.5, this one, illustrates the degree of emission control afforded by a three-way catalyst on an engine running very near the stoichiometric ratio. You can see that if the air-fuel ratio stays from lambda equals 1, the proportion of exhaust gases, hydrocarbons, carbon monoxide, nitrogen oxide exiting the converter changes. As the fuel-air ratio becomes leaner, the hotter combustion temperatures causes increased production of right. Yeah. Increased production of nitrogen oxide. A rich mixture will reduce an excess of hydrocarbon and CO. Right. So you're saying, right, so if you go, this is basically, if you've got a leaner mixture of, if you've got a lean mix, it's hotter and then you get more nitrogen oxide. If it's a weaker mixture, you're just wasting hydrocarbons and you're producing more incomplete carbon dioxide. When the air-fuel ratio is maintained at lambda equals 1, the ideal air-fuel ratio, the emission of all three pollutants is reduced to very low levels. Precise control, however, is really important to the successful operation of the three-way converters. Any significant deviation from lambda equals 1 upsets the balance of the chemical reactions in the converter, and the level of one or more pollutants increases dramatically. Development of three-way catalytic converters has been accomplished by development of of more sophisticated systems for fire control of air-fuel ratio. Okay, thanks for watching. This video's got quite long, but I'll come back to that chart and sort that out. We basically worked out that, so if you've got a lean mixture, you get more hydrocarbons and more carbon monoxide, and if you've got a rich mixture, you've got more hydrocarbons and more carbon monoxide, and if you've got a lean mixture, you get more nitrogen oxide because the temperature goes up. Didn't know that. Hope you enjoyed the video, and please please watch the one I did from the chemistry A-level book, because that's got more stuff about it in there as well. Sorry about my presentation of the vids. I'm starting to get a bit tired, having some health problems, but I wanted to put these videos out so we can keep on learning together all the things. Been really interesting, hasn't it, learning it? So hopefully you found it interesting. Please like and subscribe to the channel. Please like the video, subscribe to the channel so I can make more. Please leave some positive comments if you can. That help me out, encouragement. If you have any questions, can you ask them as well below? Then I'll try and answer it. Thanks a lot for watching. I hope you enjoyed the video. See you in the next video. We're going to finish off the chapter with control systems. Thanks. Bye.